Okay, so now let's combine all these guys into a bus. Let's create this bus here. We'll have 6 signals. Let's remember all the signals that go into a bus. Let's name them so they keep with the name throughout our blocks. Okay, now we're gonna have to convert all these signals from the stability axis that they are derived to the body axis, because all the forces that we're gonna add up in the equations of motion block, they are referenced in the body frame, and all these coefficients were derived either from wind tunnel tests or from theoretical data for the stability axis. So let's convert them to the body axis. Okay, so now before we implement our coefficients in the aerodynamics block, we need to convert them to the body axis. So they were derived in the stability axis, and we need to convert them to the body axis. So if we extend this line here, we're gonna have our drag force. So this is our CD, so it's in the same direction of the x, but in the negative sense, the perpendicular direction of the x-axis. So in the z-axis here, we have our lift. So the lift coefficient is here. And if I want to convert it to the body axis, as you can see here, we need to get this component here from the CD, and we also need this small component here from the CL. So as we can see, we have that since we have a positive x pointing forward here, the CL component is going to be a positive one, and the CD component is going to be a negative one. So if we write here, so the CX body, it's going to be the negative here, so it's going to be a positive CL, so CL times the sign between the axes, which is alpha, so the sign between the axes here, so sine alpha, and minus CD cosine alpha. Now in a similar way, if I want to have the Z component in the body axis, so Z in the body, so the CL is in the opposite way, so it's going to be a negative CL, since the Z is positive pointing down, times the cosine of alpha. And now the CD, which is pointed here, is also going to be negative, right? Since you see the projection of the CD vector in the Z body axis here is pointing in the opposite side from the positive, so the negative side, so minus CD sine alpha. So this is the first two that we got. As we can see, the y body and the y stability axis are the same. So all the vectors that are pointed in the y, they do not need any correction. So the cy body is just the same as the cy stability. And of course, the CL and CD here are also in the stability axis. So they're all here, stability axis. Okay, so these are the force coefficients. Now we need the moment coefficient. So as we saw, the moments are just vectors. So for instance, the CM vector is a moment around the y-axis, which means that we have a vector that points in this direction. So since it's in the y direction, Cm body is just the same as the Cm stability. It's the same rationale here for the Cy. For the rolling moment coefficient, which is a moment around the x stability axis here, so we have a moment so this is the CL vector here. So we have to do the same calculations that we do here. So it's going to be the CL body. It's going to be the CL. So we have CL here, and we have the Cn here. So as you can see, the Cn will generate also a rolling motion in the body axis, because if you project this guy here, it's going to be a negative contribution. So we have a positive contribution from the CL in the stability axis, and we have a negative contribution from the Cn. So it's positive CL stability times cosine alpha minus, since it's a negative contribution, minus Cn in the stability axis sine alpha. And in a similar way, the Cn body is going to be, so if I project this guy onto the Z body, it's going to be a positive projection, right? So it's going to be pointing down here. So it's a positive CLX sine alpha. And of course, the Cn is also positive, so there's a positive CNS cosine alpha. So now we have the moment coefficients conversion here, and we're gonna implement this conversion in Simulink. So in order to convert these guys, we're gonna need to unmux them. So just select all the signals. Okay. We're also gonna need the, let's create a subsystem here. This is gonna be the conversion from the stability to body. And all the moments that we derived are at the 25% chord. So let's just emphasize that. So this is the stability to body conversion at 25%. And then we're gonna add the effect of the CG. This guy here, they are the aero coefficients. We're also going to need the angle of attack to convert, as we saw on the lesson. Let's grab an angle of attack signal here that we already have. Okay. And since we're going to do the sine and cosine of the angle of attack a lot of times, so in order to help us here, let's use the from and go to blocks. This is all I call sine A to remind me of sine of alpha, and this is going to be cos A, the cosine of alpha. Okay, so as we saw, let's create our body coefficients vectors here now. We're going to need several products. So we're going to multiply the cosine of alpha times the CL. So let's start with the x coefficient, so x body coefficient. So it's going to be the minus CD cosine alpha cosine of alpha is here, and plus CL, so it's positive here, positive CL sine of alpha. Okay. And I'm gonna need we're gonna need a negative sign in the CD here, so it's -1 here. And if I add them, I'll end up with this is gonna be CX body. I'm gonna need a similar one. It's gonna be the CZ. So the CZ in the body is minus the CL times the cosine here. So let's swap these guys. Minus CD sine of alpha. If I sum them, I'll get the CZ body. Okay. So the CY body is just the same as the CY stability. CY body here, the same. And we also know that the moment coefficient is also the same. So the Cm, each moment coefficient Cm is equal to Cm body. And I will have to do a similar calculation for the CL and the Cm. So let's get these guys here. CL body. So the CL body is going to be the CL stability. So this guy here. And the Cm stability. So it's going to be positive CL stability times the cosine of alpha. So and here is going to be the sine of alpha, of course. So the CL body is just the CL stability times cosine of alpha minus Cn stability times the sine of alpha. Yeah, this guy's gonna get the CL stability. And in a similar way, we'll have the Cm body. Now we'll have both of them positives. Okay, so I have the CL stability times the sine of alpha plus the Cn stability times the cosine of alpha. We get the Cn body. Okay, this is our conversion now, so you guys can check the results. Now we have all the coefficients in the body frame, and now we just multiply by the dynamic pressure times the wing area for the forces, and an additional multiplication of the characteristic length for the moments, and we'll have the forces and moments in newtons and newtons per meter. Now we're going to do our CG corrections for the moments. So all the moments that we derived, they are derived at 25% of mean aerodynamic chord. So we have a wing here, we have a quarter chord line here, which we call a 25% quarter chord line. And all the moments derived in wind tunnel or through theoretical data, they are moments with respect to this. So we have the mean aerodynamic chord here, and they are with respect to this 25% chord line here. But the CG of the aircraft can vary in a region that we call the CG travel range. So the CG, it can vary for a given load of the aircraft, for a given passenger and cargo distribution in the aircraft. The CG can vary within limits, within predefined limits that affect the moments of the aircraft. And we have to correct the moments that we derived for a single position to any position that we might have in the aircraft. So the CG can vary in this travel range, and we have to correct them. This is the quarter chord line in our aircraft. And for instance, let's analyze the CG here. So the CG is, this is what we're gonna call delta x CG. We also need a Z reference here. So let's say that my reference of the aircraft is right here in the plane of the wing, which is normally is. So we have this data, we have this length here that we call the ZCG position, so the position of CG. And follow the same convention that we have, it's a negative CG if it's up from the origin. So let's say the origin is here, so 25% and the wing plane. So here we have a negative ZCG, and if it's below we have a positive ZCG. And now we need to convert the moments generated, so the force, the Z force is here and the X force is here. So as we can see, in addition to the moment coefficient that we have, these forces will also generate a moment with respect to these CGs here. So what will these forces be? So the moment around the CG of the aircraft is going to be the moment at 25% line. And here we have, if we have a positive pitching moment, it's going to be a positive sign here. If we have a negative pitching moment, it's going to be a negative sign here. So for instance, here we have positive, we have a delta x times this force here, and if the CG is F, as we can see here, this force is going to generate a positive pitching moment. So a negative Z force will generate a positive pitching moment. So it's going to be plus delta x CG times, and remember, this force here that I do is in the negative sense, so we have to put minus Z here. And as I drew here, we also have a negative X force. When multiplied by this lever arm here, it's going to generate also a nose down pitching moment. So to generate a nose down pitching moment, so I'll put the negative sign here times the ZCG times negative X. So the moment around the CG is going to be the moment at 25% plus X times ZCG minus Z times delta X CG. Okay, so let's just take a look at this guy here so we can see how we calculate them, how we calculate it. So this is very easy because often we specify the CG of the aircraft. So it's something like 30% of the mean aerodynamic chord. It's usually referenced like this. So we just have to subtract this guy from the reference that we have, which is a quarter chord, and multiply by the chord, and we get a length. So delta x CG is just the CG minus 0.25 times the characteristic. And this is going to be in meters, and the ZCG here is also going to be in meters. We're going to work with international standard conditions. So now we just do the same thing for the lateral coefficients, for the rolling and yawing moments. So just correct them, and remember, when we work with those moments, we have also the YCG. So usually we're gonna consider that the YCG, so the lateral CG of the aircraft, is balanced, so it's gonna be 0. It's gonna be right at the center of the aircraft. But for the ZCG, as we saw, we do not have that. So let's check the other ones. Okay, so now we have our 25% chord line here, and we have our Y force here. And for instance, let's say we put the CG here, just for an exaggeration. So here I'll have the delta x CG as we just saw, and here I'll have the phi CG. So this is going to generate a yaw moment. So the moment around the CG is going to be the moment at 25%. So let's see here. So by the right hand rule, this guy here will generate a positive Cn. So this is going to be a positive force times a positive value here. It's going to generate a positive guy here. So it's plus y times delta x CG. And we also have the, say we have the drag force here. So this guy here with respect to the CG, so this distance here, YCG. So as you can see, this force times this lever arm here is going to generate a negative yawing moment. So this generates a positive one and this generates a negative one. But remember, the x is positive in this sense here. So x body here is positive in this sense. So this is a negative x. So it's going to generate a negative yawing moment. So it's a negative yawing moment. But a negative force generates this negative yawing moment times YCG. YCG 5% plus Y YCG plus X. Okay, so now let's check our last one. So let's put the CG here just as an exaggeration. So this here is the ZCG. And this here is the YCG. So here we have our Z force. Here we have our Y force. And just to remember, here is the Z body axis and here is the Y body axis. So as we can see, the rolling moment coefficient around the CG is going to be the rolling moment at 25%. And now let's see here. The Y force times this lever arm here is going to generate a negative rolling moment. So by the right hand rule, when the right wing tends to go up, that's a negative rolling moment. So this is the right wing tending to go up. So it's a negative rolling moment. So negative rolling moment generated by a positive force. So it's y times the ZCG. And now this force here, so it will also tend, the Z force will also tend to generate a negative rolling moment. So it's going to be a negative rolling moment. But the force that's generating this negative rolling moment is also a negative force because it's pointed in the opposite side of the positive Z body axis. So it's a negative force times the lever arm here. So final equation is going to be now we implement all these three conversions in Simulink. So as we saw, to calculate the forces, we just multiply by the dynamic pressure times the wing area, and for the moments, we also need to correct for the CG. So the CG here, that we normally derive the aerodynamic coefficients are in the 25% of the mean aerodynamic chord. But when we fly, we can have CG varying around this value, so we need to correct them, as you saw on a previous lesson. So let's multiply here by the wing. So this is the, actually here it's let's show the name here just to show that this is the main area. And this is meter squared. Okay. And for the dynamic pressure, we will need the density and the true airspeed right from here. Okay. So the definition of dynamic pressure is half the density times the square of the velocity. So let's grab a multiplication block here. And here in the density I can put again and multiply it by half, so 1/2. This here is our dynamic pressure in Pascal. Now I'll multiply these guys here, and we'll have Q times S. Here we have the X aero in newtons, so our first force, Y aero newtons, and now Z aero newtons. Now for these guys here, we'll need to convert the CG. So okay, first let's do the CM, but as you can see here, I was almost making a mistake. As you can see, we have X, Z, and Y. They are not in order. And here we have Y, X, Y, and Z. So let's put them in the order X, Y, and Z, and L, M, N, because when we create our vectors, that's going to be important. In order to do that, it's just easy. So I want the X to be the first one, that's correct, but I want the Z to be the third one. So I'll just change the port number here to the third one. So now the Y is the second one, that's okay. And I want the L to be the fourth port. And M5, okay, now it's okay. As you can see, let's just reroute the signal here. So here's the Y, and here's the Z. Okay, so now I have the Z with the Z, the Y with the Y, and the X aligned with the X. So let's first, since it's easier, let's correct the CG for the CM. So as it was derived in 25%, let's correct it to the actual CG of the aircraft, the ZCG and the XCG. So the CG is also an input. Let's have the longitudinal CG, what we call the XCG. Let's create this input here. So the CG, this is going to be defined by the user, so it can vary greatly, the CG, so it's going to be defined by the user. So we have the CG here as an input. We'll have the ZCG, so the ZCG is kind of fixed, so we can just declare it here. So Z CG in meters, as we saw. So I'll call it ZCG. Okay. And the calculation that we saw is that we're gonna multiply it, the Z aerodynamic force times the CG, and this is a percentage of the aerodynamic chord, but we need a length to create a moment here. So the length is going to be in meters, and we have to convert as we learned in the previous lesson. So this is going to be the input, which is just 1 minus 0.25 multiplied by the reference chord C. And we have to add with the x-force components. And what comes out here is the M aero in newtons meter. Let's create a mini subsystem here. So this is the M 25% to CG converter. Let's just name everybody here. So this is the CG. This is the Z aero in newton. And this is the X aero in newton. So the aerodynamic moment in newton meter. Well, I forgot to add the most important, which is the moment itself. So we'll need to add the moment here at 25%. So we need to add the moment here. So it's the CM body. Okay, but actually what I need here is not the moment coefficient, is the moment itself. So let's calculate the moment before. So we'll have to multiply this guy here by the dynamic pressure, but we'll need an additional gain here, because when you talk about the moments, it's not only the dynamic pressure times the wing area, we also need the reference coordinate. Now we're gonna need a similar approach to convert the other CGs. So let's just copy this guy here and do it for the others. No longer need this. Let's create a subsystem here. So it's gonna be M 25% to CG. So for the N, we'll need of course the N moment, but we're also gonna need the Y force here and the X force. We're gonna need the CG one more time, and now we're gonna need the YCG. We're gonna need the YCG now instead of the ZCG. So it's gonna be Y. So it's the YCG times X, XCG times X. So X force times Y, and the Y force times the XCG. So we're correct, and we sum them up. So this is the N body in newtons per meter. This is gonna be an aero. And now the reference length is B. Let's do it for the L moment. That's the first one. So this is gonna be L 25% to L 25% to CG. We're gonna need the Y and the Z for this one. We'll not need the CG anymore. Just need the Y and the ZCGs here. And here we're gonna need the L. This is gonna be L. It's gonna be L. So for this guy here, so this should be Z times Y, and it's a negative sign here, so z times y is negative, z times y negative, and also need the y times z also negative, so it's also with a negative sign here. For the moment here, we have to correct because the sign here is mistaken, so this should be a negative sign because the moment generated here is in the opposite sense, it's negative, so it should have a negative sign here. Okay. So now let's just connect everybody here. So the y here, the z here. Let's calculate our moment here. Definitely don't have to increase this because it's getting too crowded here. So okay, so it's a little better now. So now let's mux all of these guys and create our aerodynamic vector. Let's put an output here, which we'll call aero forces moments. This is our final aerodynamic block here. The very complicated one with a lot of conversions. And I recommend you guys to check every step here and see if your results are comparable to mine. And hopefully when we connect everything in our final model, everything works out. So thank you guys for watching. See you in the next lesson.